Hello students, how are you all? Cello, today we're going to start a very interesting topic from our Unit 13, Nuclei. The topic is radioactivity. I know, the name itself can sound a little intimidating, and many students find it difficult. But bilkul tension maklo. In this explainer, we will break it down so simply you'll find it very easy. And everything will be perfectly exam safe. So, let's begin. So, let me start with a simple question for you. You must have seen those small plastic discs on the ceilings in many buildings, right? Smoke detectors. They just sit there, quietly. But have you ever stopped and wondered, how do they actually work? I mean, how do they magically know when there's smoke in the air? Well, the answer to that question is the key to understanding radioactivity. You see, the secret is that inside every single one of those smoke detectors, there is a tiny, tiny amount of a special element. This element is called americium-241. And the interesting thing is, it's radioactive. Yes, you heard me correctly. There is a radioactive source working silently in millions of homes right now. Now, naturally, this brings up two very important questions. First, if it's radioactive, shouldn't we be worried? Is it safe? And the second, more fundamental question is what makes something like americium radioactive while the plastic box around it is perfectly normal? To get to the bottom of this, we need to travel deep, deep inside the atom. You see, the whole story of radioactivity doesn't happen with the electrons or in the chemical bonds we've studied. No, it's hidden deep within the heart of the atom, the nucleus. So let's zoom in right past all those electrons, straight into that tiny, dense core. Inside the nucleus, there's a constant battle going on. It's like a tug-of-war, a cosmic fight between two of the most powerful forces in the entire universe. If you can understand this one battle, you'll understand everything about radioactivity. To make this really simple, let's use an analogy. Just imagine the nucleus is a tiny, tiny room. I mean, so incredibly crowded and small that it makes the head of a pin look as big as a football stadium. Now, inside this tiny room, you've packed all the protons. And you remember from electrostatics, right? Like charges repel. So all these protons, being positively charged, they just can't stand each other. They're constantly trying to push each other apart with tremendous force. We call this force Coulomb repulsion. But there's another force at play, a much, much stronger force we call the strong nuclear force. Think of it like a super strong Fevicol, but it has one condition. It only works when the particles are extremely close, almost touching. And it's this superglue that holds the nucleus together, fighting against that massive repulsion. For most atoms, this balance between the pushing force and the pulling glue is just perfect. The nucleus is stable, happy, and can stay that way forever. But what happens if the room gets too big, or if there are just too many protons all trying to push each other away? Well, the balance breaks. The strong nuclear force, because it's so short range, can't hold everyone together anymore, and the nucleus becomes unstable. And this situation, right here, brings us to the formal NCERT definition. Now, this is very important for your exams, so listen carefully. Radioactivity is a nuclear phenomenon in which an unstable nucleus undergoes a decay to become more stable. In simple words, it's just the process of an unstable nucleus trying to find peace. It wants to settle down into a lower energy, more stable state. And to do that, it has to change itself. Remember, this is a nuclear phenomenon. It has nothing to do with chemical reactions. Okay, so an unstable nucleus wants to become stable. But how does it do that? It can't just magically become stable, right? It has to actively get rid of something, either some of its particles or some of its extra energy. And in nature, there are three main ways a nucleus can do this. We call them alpha decay, beta decay, and gamma decay. Think of these as three different strategies that the nucleus uses to calm itself down. Let's look at each one by one. First up, we have alpha decay. This usually happens in very heavy nuclei, those really overcrowded rooms. The nucleus basically decides, I'm just too big and heavy. So what does it do? It throws out a small chunk of itself. This chunk is a bundle of 2 protons and 2 neutrons. Now, this package is actually a helium nucleus, and we call it an alpha particle. By getting rid of this heavy particle, the original nucleus becomes a little smaller, a little lighter, and a lot more stable. The second strategy is beta decay. Now, this happens when the problem isn't the size of the nucleus, but the ratio of neutrons to protons. It's not balanced. So if there are too many neutrons, one of the neutrons inside the nucleus cleverly transforms itself into a proton. But wait, to keep the charge conserved, a high-speed electron is created and immediately ejected from the nucleus. This fast-moving electron is what we call a beta particle. The result? The nucleus now has one less neutron and one more proton, which might just be the perfect, more stable combination it was looking for. And finally, we have gamma decay. You see, sometimes after an alpha or beta decay has happened, the nucleus is still left with too much extra energy. It's in an excited state. Think of it like a person who is really hyper and needs to calm down. So to relax, the nucleus releases this excess energy as a burst of pure, high-frequency electromagnetic radiation. This little packet of energy is a high-energy photon, and we call it a gamma ray. The nucleus doesn't lose any particles this time, it just releases energy and finally settles down into a peaceful, stable state. All right, now that we have the basics down, let's talk about some common mistakes. I call these silent killers because they seem logical, but they're completely wrong, and they can quietly cost you marks in your exams. So please pay very close attention here. The biggest myth is that all atoms and all nuclei are radioactive. This is absolutely not true. In fact, it's the opposite. Most of the nuclei in the universe are perfectly stable. The oxygen you're breathing right now, the carbon that makes up your body, most of it is made of stable isotopes that will never, ever decay. They're as stable as rocks. Radioactivity is the exception, not the rule. It only happens in certain specific unstable isotopes. The second big myth is that bigger means stronger or more stable. It's easy to think that a heavy nucleus like uranium must be much stronger than a light one like helium. But actually, it's often the other way around. Remember our analogy? The strong nuclear force, the glue, is very short range. In a huge nucleus, protons on opposite sides are too far apart to feel this glue, but they can still feel the long-range repulsion from all the other protons. So in these really big nuclei, the repulsion starts to win the battle against the strong force, and that's what makes them unstable. Okay, let's bring all of this together now. We'll summarize the key points and see how this topic connects to the bigger picture of physics. This is really important for a complete understanding. So why is this idea of radioactivity so important? Well, its discovery completely changed how we saw the world. Before this, scientists believed that atoms were permanent, that they couldn't be changed. But radioactivity proved that atoms could change all by themselves. One element could spontaneously turn into another. This incredible idea forms a bridge, connecting what we learned in the atoms chapter to our next huge topic, nuclear energy. So, for your exam, what are the key takeaways you absolutely must remember? Let's quickly revise. First, radioactivity is simply the breakdown of an unstable nucleus. Second, the cause is a battle between the strong nuclear force and Coulomb repulsion. Third, the three types of decay are alpha, which releases a helium nucleus, beta, which releases an electron, and gamma, which releases a photon of energy. Fourth, the whole goal of decay is to release energy and become more stable. And finally, please remember, most nuclei are stable, radioactivity is the exception. And all this learning leads us to a very fascinating question for our next session. We now know that unstable nuclei like uranium fall apart on their own and release energy. But what if we could take a large but more or less stable nucleus and give it a little push? Could we force it to break apart and release all that energy on our command? The answer to that question is a definite yes, and that process is what we call nuclear fission. It's the science behind nuclear power plants and atomic bombs, and that is exactly what we are going to break down in our next explainer. See you then!